Hello everyone. So in the last video, we said that if we have a continuous function on a closed bounded interval, then the absolute max and the absolute min always exist. So there always are absolute max and absolute min, but it didn't tell us how to find them. So in this video, I want to develop, a way for how do we find what is the absolute max and what is the absolute min of the function. And there's going to be a pretty clear-cut method called the closed interval method, which will be a sequence of steps that we're always going to follow for any problem like that. So before we can do that, we need to narrow down a little bit where are the absolute max and absolute min. So in the last video, we said the absolute max and absolute min can occur either at the endpoints or they can occur at the local max and the local min. So let's narrow down a little bit where the local max and local min happen before we state the closed interval method. Okay, and here's a theorem that's called Fermat's theorem. It says that if f has a local max or a local min at C, and f prime of C exists, then the derivative at C must be 0. So if the derivative exists at a local max or local min, then the derivative must be equal to 0. And here is a kind of picture that just simply, maybe not very eloquently, but simply demonstrates why it's true. If you have a local max, it kind of looks like this shape. It's like a sad face, I guess. But at the local max, this is the very top. Here the function is flat, so the derivative has to be 0. And the same thing with a local min, which is a smiley face. The local min is at the very bottom. Okay, and there it's flat. So the derivative should be 0 if it exists. Okay, and maybe an easier way or a nicer way to restate this is that if f has a local max or a local min, then either the derivative does not exist, or if the derivative does exist, then we're back up here and the derivative must be equal to 0. Okay, so stated this way, it's very nice because we're saying if we have a local max or a local min, either the derivative does not exist or the derivative equals 0. Okay, but we have a way to narrow down what these points on the right side are, right? We can see from our function, if we look at it, where the derivative does not exist or where the derivative equals 0. If someone gives you a formula for your function and they don't give you the graph, if they give you the graph, then it's easy to pick out from the graph where the local max or the local min is. But if they give you a formula and you don't have the graph, it's very hard to figure out where the max and min are. In that case, we should look at where the derivative does not exist or where the derivative equals 0. Solving derivative equals 0 is an equation that we can handle. Okay, but this is saying the local max and min lie among these points on the right side, but it doesn't say that every point on the right side is a local max or a local min, right? So it helps us to narrow down where the local max and local min are, but it doesn't tell us all the points that are local max and local min. Okay, so let me say a few words of caution. So we have to allow for the fact that f prime of C might not exist at the local max or local min. So we have to include f prime of C does not exist. For instance, if we consider absolute value x, which is a v shape, it has a local under global min at 0, but it's not differentiable at 0 because it has a corner there. Okay, so we have to include this possibility that f prime of C might not exist when we search for our maximum and minimum. And the reverse statement is not true, as we just said. So local max and local min lie among these points, but not every of these points on the right is a local max or local min. For instance, if we consider f of x equals x cubed, if you differentiate, you get 3x squared. At 0, that's going to be 0. But if you think of what the graph of x cubed looks like, at x equals 0, it's not a local max. It's not a local min, not a local max. And it's not a global min or a global max. Right, x cubed, if you move to the left, it becomes negative. If you move to the right, it becomes positive. So this point will be nothing. So just because you have the derivative equals 0, that does not tell you it's a local min or a local max or a global min or a global max. You have to do something else. So we're going to study a little bit later how to figure out, which of, when the derivative equals 0, it tells you that it's local max or local min. But for this time, we're going to focus on absolute max and absolute min. Okay, so what do we do? So these points are still useful because they at least, even if they don't tell us exactly where absolute max and absolute min and local max and local min are, they at least help us to narrow it down a little bit, right? We don't have to think about all the points. We just have to think, okay, what are the points like this? Okay, and then we can scratch our heads and think about it a bit harder when we have fewer points to think about. So the things with this property are going to be called critical numbers. So critical number is a number where either the derivative does not exist or where the derivative equals 0. And we just said that the local max and local min, they lie among the critical numbers. Okay, as we said. But not every critical number is a local max or local min. So later, we're going to need more tools to figure out which critical numbers are local max and local min. Let's focus on the absolute. So to figure out the absolute, we're going to follow this sequence of steps. So what do we have to do? We said that absolute max and absolute min, they are either endpoints or they are local max and local min. Okay, but now that we managed to narrow it down, we can just compute all the function values at those points and pick out the largest one. and compute all the function values at those points and figure out the smallest one. And that's going to give us the absolute max and absolute min. Right, once we narrow down the possibilities, whether absolute max and absolute min to just finitely many points or just a small number of points, we can manually check to see which is the largest one and which is the smallest one. Okay, so let's do that more elegantly. So here's an algorithm or a sequence of steps of how to find the absolute max and min of a continuous function on a closed interval. So that's going to be a pretty classic problem that you'll see many times from this section. Okay, so we start off by finding the critical numbers of f. So remember, the critical numbers are these ones, either where the derivative does not exist or where the derivative equals 0. So you would have to solve f prime of c equals 0. Okay, then we compute the values of f at the endpoints and at the critical numbers. Okay, and then the largest of those is the absolute maximum, and the smallest of those is the absolute minimum. Okay, and that's it, straightforwardly. So let's try to do this on some examples. Okay, so we're trying to find absolute max, absolute min of a function on a closed interval. We're going to start off by finding the critical numbers, which are where the derivative does not exist or where the derivative equals 0. Then we're going to find the value of f at the endpoints and at the critical numbers. Then we're going to choose the largest one and choose the smallest one. And as for why this works, remember we said absolute max lies among either the endpoints or among the local max. So it has to be at one of these numbers, right? The absolute max has to be at one of these numbers. And then we just pick the largest one. Okay, the largest one has to be the absolute max. And same for the other side with the minimum. Okay, so going away from the theory, let's go to the example, what we actually need to do. So let's try to find the absolute max and min of this function on the closed bounded interval 0, 5. Right, so it's a continuous function on a closed bounded interval. Find the absolute max and absolute min. If you ever see a problem like this, 99% sure that you're going to have to use the closed interval method. Okay, so remember the closed interval method. So what do we have to do? We have to find the critical numbers, right? So we have to solve either where the derivative does not exist. Okay, it's a polynomial, so the derivative exists everywhere, so we don't have to worry about that. Or we have to find where the derivative equals 0. So the derivative, if we differentiate, we get 4 minus 2x. If we solve that equals 0, we get 4 equals 2x, x equals 2. So there is exactly one critical number at x equals 2. So that was step 1, we found the critical numbers. And then the next step was to evaluate the function or find the values at the critical numbers and at the endpoints. So here I computed, if you trust me, you can always check if you like, but I just computed the value of f. So we're subbing back into the original function f, the critical numbers and the endpoints. So the critical number was 2, we get f of 2 equals 16. The endpoints was 0 and 5, right? So we get f of 0 is 12 and f of 5 is 7. So that was step 2, right? We find the value of our function at the critical numbers and at the endpoints. And then we have to choose the largest and the smallest. So we have to choose the largest of these. Okay, that's 16. So the absolute max is 16 at x equals 2. And then we choose the smallest, which is 7. So the absolute min is 7 at x equals 5. Okay, and that's all we have to do. Right, so we look for the critical points. We have to look for when the function does not exist or where the derivative equals 0. We find the critical number x equals 2. Then we compute explicitly the value of the function at the critical numbers and at the endpoints. So here were the computations. Then we pick the largest one, that's the absolute max. So 16 is the absolute max. We pick the smallest one, that's 7, that's the absolute min. So notice here that we have to check both the endpoints and the critical numbers. So it's not sufficient just to do the critical numbers. That is a really common mistake people make. They compute the critical numbers, they compute the value of the critical number, it's great, but then they don't do the endpoints. So notice here that the absolute min, for instance, was at an endpoint. So please don't make that mistake. It seems simple now that that's a clear mistake, but if you have more than one critical number, then it's really tempting just to do the max of the critical numbers and the min of the critical numbers. So please do not forget critical numbers and endpoints. Okay, so this was a pretty prototypical example, that you'll probably see on a test or a homework or something like that. Let's do a harder example, and it's not going to be harder because the steps are different. The steps are going to be the same. It's just that the function is more complicated and the solving is more complicated. So here's a tricky example, but the steps are the same. So let's try to find the absolute max and the absolute min of f of t equals 2 cosine t plus sine 2t on the interval from 0 to pi over 2. And let me just emphasize that it always matters both what the function is and what the interval is, right? So we also want to make sure the critical numbers are in the interval, and we use the endpoints of the interval. It's no good having critical numbers that are not inside the interval, right? So when we solve f prime of t equals 0, we want to make sure we only pick solutions inside 0, pi over 2, right? And similarly in whatever problem you're working on. Okay, so let's get started. So clearly it's derivative everywhere. It's differentiable everywhere rather. It's a trig function. So we have to differentiate and solve when the derivative is 0. So if we differentiate, derivative of cosine is minus sine, so we get minus 2 sine t. Derivative of sine t is 2 cosine 2t, so we get 2 cosine 2t. And then we have to solve minus 2 sine t plus 2 cosine 2t equals 0. And that's quite tricky to solve. Okay, but there is a trick here that if you have these double angles involving cosine, you can expand it using the formula cosine 2t equals 1 minus 2 sine squared t. Okay, so if you trust me, I replaced cosine 2t by 1 minus 2 sine squared t, moved that in here, distributed the bracket, cleaned up all the terms. Okay, I didn't want to make it too messy. I want to keep my slides as beautiful as possible. But okay, you can check. You will get minus 4 sine squared t minus 2 sine t plus 2. Okay, why did I want to write it this way? Well, this way it's a quadratic in sine t, right? So here I have minus 4 sine t all squared minus 2 sine t plus 2. For instance, if you were to let x equal sine t, you would have minus 4x squared minus 2x plus 2, right? You would have a quadratic equation involving x. So now we can actually solve this using the quadratic formula. Okay, so you can either make substitution if you like, or just know that it's a quadratic in sine t. So we can use quadratic equation minus b, so b is minus 2, minus b is 2, plus or minus the square root of b squared, which is 4, minus 4ac, so minus 4 times minus 4 times 2 gives us 4 plus 4 times 4 times 2, all divided by 2a, so a is minus 4, 2 of that is minus 8. Okay, so there are two solutions, or two possibilities. And if you simplify this, okay, this is 32 plus 4 is 36. Take the square root, you get 6. Okay, so if you don't like the arithmetic, you can trust me that this is what we get. So there are two possibilities, right? We can either take the plus or take the minus. So we can take 2 plus 6 is 8 divided by minus 8 is minus 1. Or we can take 2 minus 6 is minus 4 divided by minus 8 is going to be 1/2. So now we figured out what are the possible values of sine t. We try to solve these and figure out what t can be. But now it's important to remember that we're looking for values of t inside 0 pi over 2. Okay, so let me stress one more time, try to remember that when we solve for critical numbers, we're only interested in critical numbers inside the interval that we're working within. Okay, so here we're looking within 0 pi over 2. So in particular, there are no solutions to sine t equals minus 1 inside 0 pi over 2. So in 0 pi over 2, sine is always non-negative. So it's between 0 and 1. So it cannot be equal to minus 1. So this does not yield any critical numbers. So instead, we have to look at sine t equals 1/2. Unfortunately, there is a solution to sine t equals 1/2 in the interval 0 to pi over 2. There is exactly one solution, and that's pi over 6. Okay, so as we said, no solution to sine t equals minus 1, but there is one solution to sine t equals 1/2 in our interval pi over 6. Okay, and it was this way because we have to work within the interval we were given, 0 pi over 2. Okay, so this was our first step, right? We looked for the critical numbers. There are no points where the derivative does not exist. We solved and we found all the points inside our given interval where the derivative equals 0, right? We got just pi over 6. Okay, now we have to go on to step 2, which was to compute the value of the function at the critical numbers and the endpoints. So now we have the critical number pi over 6 and we have the endpoints 0 and pi over 2. So we have to compute f at those points. So let's go ahead and do that. And okay, if you want to trust me to avoid getting a big mess, for f of pi over 6, you get 3 squared, 3 over 2. For f of 0, you get 2. For f of pi over 2, you get 0. Okay, so we picked the two endpoints and the critical number. But nothing special happened. I just cleaned up the calculation. Okay, so this was step 2, right? We calculated the value of the function at the endpoints and at the critical number. And now step 3 is to pick the biggest one, and that should be the absolute max, and pick the smallest one, which should be the absolute min. Okay, so the largest one is 3 square root 3 over 2. That's bigger than 2. So the absolute max is 3 square root 3 over 2, and that occurs when x equals pi over 6. And the absolute min is, 0, and that occurs when x equals pi over 2. Okay, so we completed the problem, and we found the absolute max and the absolute min. And okay, this problem was a little tricky, but that's just because the algebra and the arithmetic were a pain. The closed interval method was always the same, right? Step 1, find the critical numbers, or critical points. That's where either the derivative does not exist or the derivative equals 0. Step 2 is to compute the value of the function at the critical numbers and the endpoints by plugging into the original function f. Step 3 is just pick the biggest thing you get out, that's the absolute max. Pick the smallest thing you get out, that's the absolute min. So it's a very clear sequence of steps. If you see any problem where you have a continuous function on a closed interval, a closed bounded interval, you're going to follow the closed interval method. Okay, and let's just revisit the key points since I feel like this was a little bit complicated. Okay, so the critical numbers are where either the derivative does not exist or where the derivative equals 0. And we said, if we have local max and local min, they are always critical numbers, but not every critical number is a local max or local min. Okay, so local max and min are inside the critical numbers, but the possible set of critical numbers could be larger. And we're going to come back to, right now, we don't know how to figure out which critical numbers are local max and local min, right? We didn't talk at all about that. So we're going to come back to that later. But for the moment, we have a way to figure out the absolute max and the absolute min, which is to use the closed interval method, right? We have to figure out these critical numbers, compute the value of the function at the critical numbers and the endpoints. The biggest one is the absolute max, the smallest one is the absolute min. Okay, thanks everyone. See you soon. See you next time. Bye-bye.